New Horizons journey to Pluto. Launch. On September 24, 2005, the spacecraft arrived at the Kennedy Space Center on board a C-17 Globemaster III for launch preparations. The launch of New Horizons was originally scheduled for January 11, 2006, but was initially delayed until January 17, 2006, to allow for borescope inspections of the Atlas V's kerosene tank. Further delays related to low cloud ceiling conditions downrange, and high winds and technical difficulties, unrelated to the rocket itself, prevented launch for a further 2 days. The probe finally lifted off from Pad 41 at Cape Canaveral Air Force Station, Florida, directly south of Space Shuttle Launch Complex 39, at 1900 hours UTC on January 19, 2006. The Centaur second stage ignited at 19:4:43 UTC and burned for 5 minutes 25 seconds. It reignited at 19:32 UTC and burned for 9 minutes 47 seconds. The ATK Star 48B third stage ignited at 19:42 and 37 seconds up and burned for 1 minute 28 seconds. Combined, these burns successfully sent the probe on a solar escape trajectory at 16.26 km per second, 58,536 km per hour, 36,373 miles per hour. New Horizons took only 9 hours to pass the Moon's orbit. Although there were backup launch opportunities in February 2006 and February 2007, only the first 23 days of the 2006 window permitted the Jupiter flyby. Any launch outside that period would have forced the spacecraft to fly a slower trajectory directly to Pluto, delaying its encounter by 5 to 6 years. The probe was launched by a Lockheed Martin Atlas V551 rocket, with a third stage added to increase the heliocentric escape speed. This was the first launch of the Atlas V551 configuration, which uses 5 solid rocket boosters, and the first Atlas V with a third stage. Previous flights had used 0, 2, or 3 solid boosters, but never 5. The vehicle, AV010, weighed 573,160 kilograms, 1,263,600 pounds, at liftoff, and had earlier been slightly damaged when Hurricane Wilma swept across Florida on October 24, 2005. One of the solid rocket boosters was hit by a door. The booster was replaced with an identical unit, rather than inspecting and requalifying the original. The launch was dedicated to the memory of launch conductor Daniel Sarikhan, who was described by space program officials as one of the most influential people in the history of space travel. Inner Solar System. Trajectory corrections. On January 28 and 30, 2006, mission controllers guided the probe through its first trajectory correction maneuver, TCM, which was divided into 2 parts, TCM-1A and TCM-1B. The total velocity change of these 2 corrections was about 18 meters per second, 65 kilometers per hour, 40 miles per hour. TCM-1 was accurate enough to permit the cancellation of TCM-2, the second of 3 originally scheduled corrections. On March 9, 2006, controllers performed TCM-3, the last of 3 scheduled course corrections. The engines burned for 76 seconds, adjusting the spacecraft's velocity by about 1.16 meters per second, 4.2 kilometers per hour, 2.6 miles per hour. Further trajectory maneuvers were not needed until September 25, 2007, 7 months after the Jupiter flyby, when the engines were fired for 15 minutes and 37 seconds, changing the spacecraft's velocity by 2.37 meters per second, 8.5 kilometers per hour. 5.3 miles per hour, followed by another TCM, almost 3 years later on June 30, 2010, that lasted 35.6 seconds, when New Horizons had already reached the halfway point, in time traveled, to Pluto. In-flight tests and crossing of Mars orbit. During the week of February 20, 2006, controllers conducted initial in-flight tests of 3 onboard science instruments, the ALICE ultraviolet imaging spectrometer, the Pepsi plasma sensor, and the LORRI long-range visible spectrum camera. No scientific measurements or images were taken, but instrument electronics, and in the case of ALICE, some electromechanical systems were shown to be functioning correctly. On April 7, 2006, the spacecraft passed the orbit of Mars, moving at roughly 21 kilometers per second, 76,000 kilometers per hour, 47,000 miles per hour, away from the Sun at a solar distance of 243 million kilometers. Asteroid 132,524 APL. Because of the need to conserve fuel for possible encounters with Kuiper belt objects subsequent to the Pluto flyby, intentional encounters with objects in the asteroid belt were not planned. After launch, the New Horizons team scanned the spacecraft's trajectory to determine if any asteroids would, by chance, be close enough for observation. In May 2006 it was discovered that New Horizons would pass close to the tiny asteroid 132,524 APL on June 13, 2006. Closest approach occurred at 4:05 UTC at a distance of 101,867 kilometers, 63,297 miles. The asteroid was imaged by RALPH. Use of LORRI was not possible because of proximity to the Sun, which gave the team a chance to test RALPH's capabilities, and make observations of the asteroid's composition as well as light and phase curves. The asteroid was estimated to be 2.5 kilometers, 1.6 miles, in diameter. The spacecraft successfully tracked the rapidly moving asteroid over June 10 to 12, 2006. First Pluto sighting. The first images of Pluto from New Horizons were acquired September 21 to 24, 2006, during a test of LORRI. They were released on November 28, 2006. The images, taken from a distance of approximately 4.2 billion km, 2.6 billion mile, 28 astronomical units, confirmed the spacecraft's ability to track distant targets, critical for maneuvering toward Pluto and other Kuiper belt objects. Jupiter encounter. New Horizons used LORRI to take its first photographs of Jupiter on September 4, 2006, from a distance of 291 million kilometers, 181 million miles. More detailed exploration of the system began in January 2007 with an infrared image of the moon Callisto, as well as several black and white images of Jupiter itself. New Horizons received a gravity assist from Jupiter, with its closest approach at 5:43 and 40 seconds on February 28, 2007, when it was 2.3 million kilometers, 1.4 million miles, from Jupiter. The flyby increased New Horizons' speed by 4 kilometers per second, 14,000 kilometers per hour, 9,000 miles per hour, accelerating the probe to a velocity of 23 kilometers per second, 83,000 kilometers per hour, 51,000 miles per hour, relative to the Sun and shortening its voyage to Pluto by 3 years. The flyby was the center of a 4-month intensive observation campaign lasting from January to June. Being an ever-changing scientific target, Jupiter has been observed intermittently since the end of the Galileo mission in September 2003. Knowledge about Jupiter benefited from the fact that New Horizons instruments were built using the latest technology, especially in the area of cameras, representing a significant improvement over Galileo's cameras, which were modified versions of Voyager cameras, which, in turn, were modified Mariner cameras. The Jupiter encounter also served as a shakedown and dress rehearsal for the Pluto encounter. Because Jupiter is much closer to Earth than Pluto, the communications link can transmit multiple loadings of the memory buffer, thus the mission returned more data from the Jovian system than it was expected to transmit from Pluto. One of the main goals during the Jupiter encounter was observing its atmospheric conditions and analyzing the structure and composition of its clouds. Heat-induced lightning strikes in the polar regions and waves that indicate violent storm activity were observed and measured. The little red spot, spanning up to 70% of Earth's diameter, was imaged from up close for the first time. Recording from different angles and illumination conditions, New Horizons took detailed images of Jupiter's faint ring system, discovering debris left over from recent collisions within the rings or from other unexplained phenomena. The search for undiscovered moons within the rings showed no results. Traveling through Jupiter's magnetosphere, New Horizons collected valuable particle readings. Bubbles of plasma that are thought to be formed from material ejected by the moon Io were noticed in the magnetotail. Jovian moons. The 4 largest moons of Jupiter were in poor positions for observation. The necessary path of the gravity assist maneuver meant that New Horizons passed millions of kilometers from any of the Galilean moons. Still, its instruments were intended for small, dim targets, so they were scientifically useful on large, distant moons. Emphasis was put on Jupiter's innermost Galilean moon, Io, whose active volcanoes shoot out tons of material into Jupiter's magnetosphere, and further. Out of 11 observed eruptions, 3 were seen for the first time. That of Tvashtar reached an altitude of up to 330 kilometers, 210 miles. The event gave scientists an unprecedented look into the structure and motion of the rising plume and its subsequent fall back to the surface. Infrared signatures of a further 36 volcanoes were noticed. Callisto's surface was analyzed with LASA, revealing how lighting and viewing conditions affect infrared spectrum readings of its surface water ice. Minor moons such as Amalthea had their orbit solutions refined. The cameras determined their positions, acting as reverse optical navigation. Outer Solar System. After passing Jupiter, New Horizons spent most of its journey towards Pluto in hibernation mode. Redundant components as well as guidance and control systems were shut down to extend their life cycle, decrease operation costs and free the deep space network for other missions. During hibernation mode, the onboard computer monitored the probe's systems and transmitted a signal back to Earth, a green code if everything was functioning as expected or a red code if mission controls assistance was needed. The probe was activated for about 2 months a year so that the instruments could be calibrated and the systems checked. The first hibernation mode cycle started on June 28, 2007, the second cycle began on December 16, 2008, the third cycle on August 27, 2009, and the fourth cycle on August 29, 2014, after a 10-week test. New Horizons crossed the orbit of Saturn on June 8, 2008, and Uranus on March 18, 2011. After astronomers announced the discovery of 2 new moons in the Pluto system, Kerberos and Styx, mission planners started contemplating the possibility of the probe running into unseen debris and dust left over from ancient collisions between the moons. A study based on 18 months of computer simulations, Earth-based telescope observations and occultations of the Pluto system revealed that the possibility of a catastrophic collision with debris or dust was less than 0.3% on the probe's scheduled course. If the hazard increased, New Horizons could have used one of 2 possible contingency plans, the so-called SPOTS, safe haven by other trajectories. The probe could have continued on its present trajectory with the antenna facing the incoming particles so the more vital systems would be protected, or, it could have positioned its antenna to make a course correction that would take it just 3,000 kilometers from the surface of Pluto where it was expected that the atmospheric drag would have cleaned the surrounding space of possible debris. While in hibernation mode in July 2012, New Horizons started gathering scientific data with SWAP, Pepsi and VBSDC. Although it was originally planned to activate just the VBSDC, other instruments were powered on the initiative of principal investigator Alan Stern, who decided they could use the opportunity to collect valuable heliospheric data. Before activating the other 2 instruments, ground tests were conducted to make sure that the expanded data gathering in this phase of the mission would not limit available energy, memory and fuel in the future and that all systems are functioning during the flyby. The first set of data was transmitted in January 2013 during a 3-week activation from hibernation. The command and data handling software was updated to address the problem of computer resets. Possible Neptune Trojan targets. Other possible targets were Neptune Trojans. The probe's trajectory to Pluto passed near Neptune's trailing Lagrange point, L5, which may host hundreds of bodies in 1-to-1 resonance. In late 2013, New Horizons passed within 1.2 astronomical units, 180 million kilometers, 110 million miles, of the high-inclination L5 Neptune Trojan 2011 HM102, which was identified shortly before by the New Horizons KBO Search Survey team while searching for more distant objects for New Horizons to fly by after its 2015 Pluto encounter. At that range, 2011 HM102 would have been bright enough to be detectable by New Horizons' LORRI instrument. However, the New Horizons team eventually decided that they would not target 2011 HM102 for observations because the preparations for the Pluto approach took precedence. Observations of Pluto and Charon 2013-14. Images from July 1 to 3, 2013. By LORRI were the first by the probe to resolve Pluto and Charon as separate objects. On July 14, 2014, mission controllers performed a 6th trajectory correction maneuver, TCM, since its launch to enable the craft to reach Pluto. Between July 19 to 24, 2014, New Horizons LORRI snapped 12 images of Charon revolving around Pluto, covering almost one full rotation at distances ranging from about 429 to 422 million kilometers, 267 million to 262 million miles. In August 2014, astronomers made high-precision measurements of Pluto's location and orbit around the Sun using the Atacama Large Millimeter/Submillimeter Array, ALMA, to help NASA's New Horizons spacecraft accurately home in on Pluto. On December 6, 2014, mission controllers sent a signal for the craft to wake up from its final Pluto approach hibernation and begin regular operations. The craft's response that it was awake arrived to Earth on December 7, 2014, at 2:30 UTC. Pluto approach. Distant encounter operations at Pluto began on January 4, 2015. At this date, images of the targets with the onboard LORRI imager plus the Ralph telescope would only be a few pixels in width. Investigators began taking Pluto and background starfield images to assist mission navigators in the design of course-correcting engine maneuvers that would precisely modify the trajectory of New Horizons to aim the approach. On January 15, 2015, NASA gave a brief update of the timeline of the approach and departure phases. On February 12, 2015, NASA released new images of Pluto, taken from January 25 to 31, from the approaching probe. New Horizons was more than 203 million kilometers, 126 million miles, away from Pluto when it began taking the photos, which showed Pluto and its largest moon, Charon. The exposure time was too short to see Pluto's smaller, much fainter, moons. Investigators compiled a series of images of the moons Nix and Hydra taken from January 27 through February 8, 2015, beginning at a range of 201 million kilometers, 125 million miles. Pluto and Charon appear as a single overexposed object at the center. The right side image has been processed to remove the background starfield. The yet smaller two moons, Kerberos and Styx, were seen on photos taken on April 25. Starting May 11, a hazard search was performed, by looking for unknown objects that could be a danger to the spacecraft, such as rings or more moons, which were possible to avoid by a course change. Also, in regards to the approach phase during January 2015, on August 21, 2012, the team announced that they would spend mission time attempting long-range observations of the Kuiper Belt object temporarily designated VN80004, now designated 2011 KW48. When the object was at a distance from New Horizons of 75 gigameters, 0.50 astronomical units. The object would be too distant to resolve surface features or take spectroscopy, but it would be able to make observations that cannot be made from Earth, namely a phase curve and a search for small moons. A second object was planned to be observed in June 2015, and a third in September after the flyby. The team hoped to observe a dozen such objects through 2018. On April 15, 2015, Pluto was imaged showing a possible polar cap. Software glitch. On July 4, 2015, New Horizons experienced a software anomaly and went into safe mode, preventing the spacecraft from performing scientific observations until engineers could resolve the problem. On July 5, NASA announced that the problem was determined to be a timing flaw in a command sequence used to prepare the spacecraft for its flyby, and the spacecraft would resume scheduled science operations on July 7. The science observations lost because of the anomaly were judged to have no impact on the mission's main objectives and minimal impact on other objectives. The timing flaw consisted of performing two tasks simultaneously, compressing previously acquired data to release space for more data, and making a second copy of the approach command sequence, that together overloaded the spacecraft's primary computer. After the overload was detected, the spacecraft performed as designed. It switched from the primary computer to the backup computer, entered safe mode, and sent a distress call back to Earth. The distress call was received the afternoon of July 4, which alerted engineers that they needed to contact the spacecraft to get more information and resolve the issue. The resolution was that the problem happened as part of preparations for the approach, and was not expected to happen again because no similar tasks were planned for the remainder of the encounter.